There we go. Okay, so we'll get right into it today because I think this proof, finishing this proof is still going to take us a little while. I'd say probably 20 to 25 minutes to get this done. That might be an overestimate, but we'll see. So just as a recap, the first assignment, which was supposed to be due this Friday, January 22nd, will now be due Monday the 25th, and then on Friday, if I still feel like you need a little more time, I'll push it again. But for now, we'll just say it's due Monday because that should be sufficient just to finish off those last few questions. And in terms of the lecture material, we are in lecture set 2, and we are working through proof that show the form of our SRS estimator. So on slide 20, we have, well, on slide 19 rather, the estimators for a simple random sample are stated. So we have the estimator for the population mean, and we have the estimator for the population standard deviation. And obviously, if we want to have population variance, we just have to square this, right? So, I mean, they're interchangeable in that sense. We introduced an indicator variable, capital I subscript I, to represent whether or not the observation belongs to the sample. And we showed on slide 20 that the estimator for mu, so mu tilde, is unbiased. And we showed the form of the variance for mu. We showed the form of the variance of mu tilde, which is 1 minus little n over capital N multiplied by sigma squared over little n. And again, that 1 minus little n over capital N is called the finite population correction. And we'll talk about that in a little more detail after. What we are doing right now is we are showing how we can prove that the expected value of mu tilde is equal to mu, and that the variance of mu tilde is equal to 1 minus little n over capital N times sigma squared over little n. So we are working through these two proofs, or we're working through the proofs of these two results currently. Last class, we started off by working through the proof for the expected value of mu tilde. For the most part, this is a pretty straightforward proof. The big difference, or the what might change the structure of this proof from expected value proof you have seen before, is that we are actually considering the yi to be a constant, but we are considering the capital I subscript I, that indicator, to be the random variable. So we actually required the expected value of I subscript little I, which we can show is a Bernoulli, as it is either 1 or 0. And from that, we were able to derive that the expected value of I subscript little I is little n over n. And once we had that worked out, the rest of the proof is pretty straightforward. So what we are going to do, or what we started to work on last class, was the proof for the variance. Now, the idea here is very similar. When we set up our equation, so for example, I have step 1 here. We have the variance of mu tilde. So this, we can think of this as kind of the starting point. So we want the variance of mu tilde. The variance of mu tilde is equal to the variance of 1 over little n multiplied by the sum across the frame of all of the yi that are included in the sample. So again, we have this capital I subscript little I here, and then we have our yi, which are the constants here. Now, when we expand this out, what we end up with is 1 over n squared. This is because the variance squares all constants that are inside of the function. And then we have two terms. We have the sum across all observations in the frame of the yi squared. Again, a squared yi, because we consider yi to be a constant, and the variance squares all constants, multiplied by the variance of what is our random variable, which is our Bernoulli random variable, plus the sum of the covariance term between observation I and observation J. All right, so to finish this proof, what we're going to now discuss is how we would work out these two required terms that I have highlighted on slide 21. So we need the variance of our Bernoulli random variable of the indicator, and we need the covariance between indicator I and indicator J. All right, so let's start. Let's just give this another little name. So we'll call this required 1, and we'll call this required 2, just so that we can differentiate between them. So we'll go in order, and we'll start with the first one. All right, so give myself a little bit of space here. So this will be required 1. Okay, so for the most part, this term is fairly easy to work out. So we'll start off by just saying, recall that I subscript little I is Bernoulli. Okay. So now we can write the variance of I subscript I is equal to the expected value of I subscript I squared minus the expected value of I subscript I all squared. All right, so we know that the expected value of I subscript little I is equal to little n over capital N. We worked that out on the previous slide. How do we work out the expected value of I subscript little I squared? Well, since I subscript little I is a Bernoulli, the expected value, which is simply the sum across all possible values of the variable multiplied by the probabilities of observing those variables, will still apply. So we can write the second term as 0 squared, so that's the first value the indicator can take on, multiplied by the probability that the observation is not in the sample. So that'll be 1 minus n over little n, which is the selection probability for that value, plus 1 squared multiplied by little n over n. Okay. So if you compare what I have written here on slide 21, and I'm just going to flip back for a second so you can see it. If you compare what I have just written here to what I have written in red at the bottom here, you can see that this is the same derivation. The only difference is that I did the 0 first rather than the 1 first, and I have to square each term. Okay. So basically here, all we're doing is making use of the fact that the expected value of x squared is equal to the sum over x of x squared multiplied by the probability of x. Okay, so that would be a fairly straightforward application of the definition of an expected value. And again, we only have to consider the two terms because we know that I subscript little I is a Bernoulli, so it only has two possible outcomes. And then we would just subtract off n over little n squared, which we worked out when we calculated the expected value of mu tilde. Okay. All right, so this, after some simplification, so obviously everything times 0 is just 0, and then you just end up with little n over capital N minus little n over capital N squared. And then here we can just factor this thing out, and we have little n over capital N multiplied by 1 minus little n over capital N. And now you can see here that FPC that we had talked about before, so that finite population correction. So you can see here where that term is likely going to come from once we complete the proof. So that's the first term that we need. So now we have the variance of I subscript little I. And now what we have to do is work out the covariance of I subscript little I. Does anyone have any questions? Sure, I think this will be fine. Okay, let's talk about this covariance term now. So the covariance of two random variables is equal to the expected value of their product minus the expected value of the, or sorry, is the expected value of their product minus the product of their expected values. Okay, this first term here, or the second term, which is the product of the expected value. So we have the expected value of I subscript I, and we have the expected value of I subscript j. Not too concerned with this because we know that these are both just little n over capital N. So we've derived those a few times already. But we need to work out the expected value of I, or of the product. Okay. And so what is this? Okay. Okay, so this particular term isn't terribly difficult to derive because we are dealing with an indicator variable. So the I subscript I is a 0 or a 1, and the I subscript j is also 0 or 1. So the first thing that we can do is we can note the product of I subscript I and I subscript j is equal to 0 unless both I subscript I equals 1 and I subscript j equals 1. Right? So to understand this, we can consider the following illustration, or the following table, I guess, if you want. Just trying to maximize my space allocation here. So I'll just put the table here. Whatever, it is what it is. Okay. And then just for clarity, we'll call this, consider the following table of products. Okay, so that initial note is basically just, that initial note is showing us the same thing the table is illustrating, which is the only time that this expected value term is actually going to exist is when both I subscript I or when observation I and observation J are both included in the sample. So if either observation I or observation J are not included in the sample, then that product doesn't exist. Okay, because you're multiplying by a zero term, essentially. So this table and that note are illustrating the same thing. Okay, does anyone have any questions about that? So therefore, the expected value of I subscript I subscript J is equal to the probability I, J are both in the sample, which is equal to n minus 2 over little n minus 2, or n minus 2 choose little n minus 2, divided by capital N choose little n, right? And then this follows from the same derivations that we did for the inclusion probability before. Sorry, I'll just give it a second in case anyone's writing this down. But from essentially what we're saying is, what is the probability that we collect a sample of size little n if these two values have to be included in the sample? Well, if those two values are in the sample, then we have capital N minus 2 choose little n minus 2 observations left to choose from over all possible samples of size little n. And if we refer back to, I'll just move real quickly here. If we refer back to slide 18, you can see our initial derivation for this probability, or for the inclusion probability, is shown here, and it's the exact same idea. I should mention too, actually, all right, so and then just for clarity, in case it's not entirely clear. So the reason that I have this as an equality here is because of the note before. So this is a result of expected value of I subscript I subscript J only existing when I equals 1 and IJ equals 1. Okay. I guess if we wanted to really be formal about it, which maybe would have been a better way, I could have written it as 0, 0 times the probability IJ not in the sample plus 0 times 1 times the probability I is equal to 1 and J is equal to 0, that kind of idea. But basically what happens is everything gets canceled out except for the case where both observations are in the sample. So that's why the probability expression here is equivalent to the expected value. And actually, to make that a little more clear, you could write leading ones out front like this to represent II and IJ. Now, at this point, I've probably gone too far trying to make sense of trying to explain what I've written here, and hopefully I haven't confused anyone, but that's the I'm just trying to give multiple reasons for the rationale as to why we can write the expected value like this. Okay, and then we can simplify this expression to get little n multiplied by little n minus 1 over capital N multiplied by capital N minus 1. And again, if we compare this to what we had for the inclusion probability of the single observation, you can see that this is a very logical result because we're just saying, okay, now we have the single multiplied by the second observation in the sample. And obviously we're just taking off a value given that we only have little n minus 2 values remaining to choose from or to choose. Does anyone have any questions about that proof or what we've written so far? Okay. All right, so now we can finish this last part off. So we have the covariance term written out above. So we have the covariance of I subscript I, comma I subscript j, which as we have written above here, sorry, I keep moving the slide, is the expected value of the product minus the product of the expected value. Okay, so this is going to be little n multiplied by little n minus 1 over capital N multiplied by capital N minus 1 minus little n over capital N squared. And this will be negative little n over capital N 1 minus little n over capital N multiplied by 1 over n minus 1. Okay, so now we have the terms that we need to complete our proof for the variance of mu tilde. So from this point on, effectively all we have to do is sub everything into the original expression, which was given at the top. All right. So I wrote that as step 1, but so we'll say, just for continuation's sake, so we'll say step 1. How did I write it there? I underlined it. Continued. All right, so we are going to have the variance of mu tilde is equal to 1 over little n squared, open large bracket. And then the first thing we're going to use is the result shown here. So in required 1. I apologize for having to scroll up and down, but as you can see, it's a long proof. Okay, so we're going to take the first result under required 1, and we're just going to sub this in to our original variance expression, which is given above. Okay, so in doing that, we will arrive at the following. So this is going to give us little n over capital N 1 minus little n over n multiplied by the sum of I in u multiplied by yi squared. Okay, so that's our first term. And then we will take our second result, which is for the covariance term. Okay, so if we consider the original variance expression again, so I'll just read to you what it said rather than having to scroll up and down, just in case someone's copying. So now what we want to do is add the sum of yi times yj multiplied by the covariance. So here we're going to have our result for the covariance. And then we're going to multiply by the sum across all I not equal to j of ij in u. So this is actually, I'll make this a semicolon. Sorry, I'll just do that on both for consistency. I was missing this above. Sorry. All right. Multiply by the sum here of yi multiplied by yj. Anyone have any questions so far? Did you guys notice that wind last night? It scared the crap out of me. All the lights flickered on and off and the windows were like shaking. I agree. It didn't last very long though. It was like 10 minutes and it sort of calmed down. No way. Was there no like, I guess, is it a propane barbecue or a gas one? Either way, I guess it must not be very heavy. Yeah, okay, that makes sense. A dumpster? It must have been empty too, right? That's crazy, man. Yeah. I'm just glad I wasn't outside at the time. That would have been brutal. All right. Okay, so I'm going to flip to a new slide here. All right, so we can simplify this a little bit. So we can write the variance of mu tilde is equal to 1 over little n, 1 minus little n over capital N, 1 minus capital N, multiplied by the sum of I in u, yi squared, minus the sum of I not equal to j. So this is a semicolon, I, j in u of yi, yj divided by n minus 1. Right. Okay. All right, now this term here, or actually here, I'll write it like this. All right, so we have note. Okay, so the sum I not equal to j of I and u, j, I comma j in u of yi, yj. This can be written as the double sum of I and u across j in u for all I not equal to j of yi, yj, which can be written as the sum I in u of yi multiplied by the sum j in u I not equal to j yj. Okay. And then this second term here, right? Okay, so this term here can be written as, so the sum, or actually I don't need the blue underline here. And then we'll have note 2. Okay, so we can re-express the sum over the product as the sum across yi multiplied by the sum across all j, such that I does not equal to j. And then this second term, so oh, sorry, one sec. Oh, I and u sorry. So this term here, so this term here can actually be written, I wrote that wrong. So this is I in u. So we have an I in u attached to the yi here. And then we have I in u again for I not equal to j, or j not equal to I of yj. Okay, there we go. Okay, that makes more sense. And then we can have I in u j not equal to I. Okay, of yj. So this is going to be y1 plus yj minus 1 plus yj plus 1 plus y little n. Right. Okay, and then this thing, this summation here, we can write or show that this is equivalent to the sum across j and u of yj minus yi, which is n mu minus yi. All right, so I'll just give that a second in case you're copying it down, and then if anyone has any questions, please let me know. But you can see like there's a couple of interesting interesting manipulations of the double sum that are going on here, and then some results that fall out from that double sum that we can utilize within our proof for the variance. Okay, so we're almost there. The last thing that we really have to do here is just simplify the second term in our covariance expression. So we've already found an expression for the double sum, or for the sum across the product of yi, yj over all I, j in the frame, such that I is not equal to j. So we can show that the sum across j of I in u, j not equal to I, is n mu minus yi. All right, now what we can show is that, so this will be note 1. Okay, note 3. All right, so so now if we combine the first two notes, I guess I should have just written these as formulas, but so now we can say, so the double sum here, or the sum of I not equal to j of I in u, j in u of yi, yj is equal to the sum I in u, u of yj multiplied by n mu minus yi. All right. And then this thing, if we solve this thing out, we can show that this is just n squared mu squared minus the sum I in u of yi squared. All right. So now, when we come back to our variance expression, we have 1 over little n, 1 over capital N, 1 minus little n over capital N. And then we have the sum I in u of yi squared minus 1 over n minus 1 of n squared mu squared minus the sum I in u of yi squared. I said 20, 25 minutes, right? What I meant to say was the entire lecture will be devoted to this proof. Okay, so that's that part. Now we're really into the simplifying stage here. So we're gonna have 1 over little n, 1 over capital N, 1 minus little n over capital N. And then here we will have capital N over n minus 1 of the sum I in u yi squared minus n over capital N minus 1 of n mu squared. Make sure I didn't miss any terms here. Okay, and then this becomes 1 over little n, 1 over capital N, 1 minus little n over capital N, multiplied by n over n minus 1 of the sum I and u yi squared minus n mu squared. Okay, and now we're at the last part. So we start to get a little bit of cancellation here. So this term is gone. This term is gone. This thing here, we can call sigma squared multiplied by n minus 1. All right. Sorry, let me just make sure I have that correct. Y squared and mu squared. Yeah, so that's sigma squared multiplied by n minus 1. Okay, so then we end up with 1 over little n, 1 minus little n over capital N multiplied by sigma squared, which is equal to 1 minus little n over capital N multiplied by sigma squared over little n. That's required. We did it. Okay. All right. So that is why the variance of mu tilde is 1 minus little n over capital N multiplied by sigma squared over capital N. Or sigma squared over little n. Now, along the way to accomplishing or to showing that that was true, I think that we touched on a lot of different things. Obviously, we worked through variance and covariance derivations. I think it's a really nice example of how the covariance operator works because it does turn out to be very clean. There's also all of these different notes about summations that are very interesting to look into. I know that even for myself, the first time I went through this, I had to prove out a lot of these, like note 2, for example, to myself to understand why it worked this way. But as I was, all of these different things you can show pretty easily. I actually have a mistake here that I need to fix up. Sorry. So these are I's, not J's. I. You're plugging in an I. There you go. All right. Now, the one big thing or term that tends to create a lot of confusion when you go back to study this proof, if you're working through it and you're trying to make sense of it so that you can understand how to apply it on a test and whatnot. This last term here, the sigma squared term, one of the things that will inevitably come up is that we're defining sigma squared to have a denominator of capital N minus 1. And we know that in practice, sigma squared has a denominator of capital N, not capital N minus 1. I wish I could provide a good rationale for why we can make this assumption or why we can write it this way. When I've talked to colleagues about it, a lot of their answers will typically be, I mean, for a large population size, it's basically the same thing, which fair enough. But I don't have a good explanation for why this is true, but this is how the proof has been done in the past. Probably because it simplifies nicely is the reason. But this will inevitably probably create an error or will create some confusion once you're working through it, because we've always defined the population variance to have a denominator of capital N. Otherwise, I think just take some time to work to go through the steps of the proof. I've tried to lay it out in as organized and logical a fashion as possible. Obviously, a lot of these subparts, so the required 3 here, where you show the expected value of I subscript I, and you have the note about why this is the case. You don't have to write this down when you're reproducing the formula. All of these like little side parts, so required 3 and whatnot, those are just for you for an understanding point of view. The same thing with the notes that are given on slide 23. So note 1, 2, 3. You don't have to reproduce this every time, but these are just written for you to understand how we're transitioning from main step to main step within the proof itself. Because I think that had I just written out the variance of mu tilde in the black font and then went from the first line on this slide to the second line, most students probably would have been pretty confused as to how I got from this sum across the product to the n squared mu squared minus the sum across I and u of yi squared, which is fair enough. I mean, I was confused about that as well. So these notes are to help with that transition. But again, you don't have to reproduce the notes. Like, this is simply for learning. In the event that you're asked to reproduce the proof, you can just work through the main parts of the proof to the solution, with the assumption that I understand how the notes and those sub-required parts operate. All right, so that's probably the biggest proof we're going to see in the course. We get it out of the way early. We're going to see a lot of proofs based off of this idea later on. As I had mentioned before, most of the different sampling schemes that we're going to talk about, they use SRS as their foundation. So the results that we have here, a lot of the time what we'll be doing later on is basically taking a sampling strategy and then reproducing it into kind of its SRS component, and then being like, oh, we already know the result here, so we can just apply that here. And then we'll end up with some different constants and whatnot. But this, I think, from my memory, is it's probably the hardest or longest proof that we'll see in the class. We'll also look at a proof for the variance of what is called it's either the regression or the ratio operator. That one is interesting too, because it uses some Taylor expansions to work it out, but it's not quite as in depth as this, I would say. Okay, so that brings us to 948. So the finite population, so in the results, I have mentioned a couple of times that we have this term here, which is the FPC, or our finite population correction. So the finite population correction, we typically apply it when when it is either greater than 0.95 or little n is less than 1 over 20 times the population size. I mean, this is the same rule. So basically the idea is we apply the FPC whenever whenever that value is greater than or equal to, or we ignore that value, we ignore the FPC whenever 1 minus little n over capital N is greater than or equal to 0.95. So basically when we're working through our problems, we'll check to see if we exceed that ratio, and if we do, then we can ignore the FPC. Okay, we can also, obviously, if we want, we can write little n over capital N equal to some constant. So we'll call it F, which we call the sampling fraction. So our estimator could also be written as 1 minus little f multiplied by sigma squared tilde over n. These are the same results. Okay, so that brings us to the conclusion of today's lecture. So as I mentioned before, we'll extend the first assignment because I actually haven't shown you guys an example of how the estimation schemes for the confidence intervals and whatnot work yet, but we will do that on Friday. I'm very confident of that. So for now, we'll just say the assignment is due Monday because those 2 questions won't take you very long. And just so that everyone's on the same page, at this point, well, question 1 you've been able to do for quite a while. Question 2, we haven't talked about a proportion yet. So question 2, maybe you'll have to wait until Friday to see some proportion examples. But if you read ahead, you could probably get this done. Question 3 you can do. Question 4 you can do. Question 5A you can do. Question 5B part 1 you can do, and 2 you can do. Question 5C part 1 you can also do. So question 5B part 3 and B part 4, the confidence intervals, and then C part 2 and C part 3, the confidence interval parts. We haven't seen an example of that yet. If you read ahead, you'll probably be able to figure it out. It's very basic confidence interval construction. But I'll definitely get to an example of that on Friday. So with that in mind, we'll just say that the assignment will be due Monday because it won't take you very long to compute the interval once you have your sample collected. All right, so I'll make a note about that and I'll send a little reminder. Otherwise, if you have any questions, please let me know. And if not, I'll talk to you guys on Friday morning. And hopefully I'll have an announcement about the whatever the new restrictions are going to be, as I think that's being made tomorrow. Okay, so have a good couple of days and I'll see you guys on Friday morning.